So last time what we did was to go in great detail these limitations of the use of the event horizon, which is of course how in the traditionally black holes are defined. And so that was part 7 last time. We just finished the shortest part. It was about limitations of the standard paradigm. For black holes, standard paradigm for black holes. And the first was that is too global. The notion of event horizon is too global. And I explained what it means. In particular, for numerical relativity, it's not very useful because we need to know the entire space-time before we can tell whether there was an event horizon. So if you're evolving black holes, that is not very directly helpful. The second thing was it is teleological. And we saw explicitly the examples of bidiametric. We'll see it again next lecture, in which, in fact, the event horizons form in a flat region of space-time, and they can actually even grow in the flat region of space-time in anticipation of a collapse that would happen much, much later, 100 million years later. And that can be happening in this room right now, that the event horizon may be forming. And so somehow that is not that useful a notion. And the third thing had to do with the equilibrium situation. Namely, the standard paradigm says that equilibrium means space-time has to be, entire space-time has to be globally stationary. Not just the black hole, not just the neighborhood of the black hole, but the entire space-time. And in fact, in many of these laws of black hole mechanics, which we'll do, in fact, one is actually assuming that the entire space-time is stationary and using structure at infinity and using the scaling vector field all the way at infinity, not to the horizon. So that's what we saw, and then we started with the next topic, which was quasi-local horizons. And then the first part we did last time, which was marginally trapped surfaces, what they are, why they are useful, how we could hope to get the notion of a black hole in terms of these marginally trapped surfaces. And now what we want to do is to continue along that line. And the basic idea I told you last time that quasi-local horizons are you can think of them as being world tubes of these marginally trapped surfaces. So it's the world tube. You stack them. You stack marginally trapped surfaces on the top of each other. You follow, quote unquote, their evolution, and you'll obtain a world tube of marginally trapped surfaces. So this will be a three-dimensional object, and this will be the quasi-local horizon. And now what we are going to do first is, so these quasi-local horizons are going to be divided into two parts. I mean, you can do simultaneously everything, but it becomes pedagogically a little more complicated. The first part is equilibrium situations, which will generalize this standard paradigm, which assumes global killing vector field. We are not going to assume any killing vector field at all. So equilibrium situation. And the other one is dynamical situation. So basically, if a gravitational collapse occurs, then during the collapse, the horizon is actually growing. The area of the marginally trapped surface is increasing, and there is a dynamical part. And then when the black hole settles down, then in fact it becomes an isolated horizon. Nothing falls across the black hole. That is the idea. So equilibrium means it's isolated or nothing falls across it. And dynamical situations is, of course, a dynamical, so the horizon is growing, or the area, the marginally trapped surfaces is increasing. For definiteness and for simplicity, when I discuss these things, most of the time I'm just referring to classical general relativity as opposed to quantum gravity. In quantum gravity, because of Hawking effect, the area can also decrease, and then something else happens. But I'll here restrict myself to classical relativity, and then at the end tell you what happens during the evaporation process. It will be fairly clear at the end. Okay, so these are the things. So these objects are called isolated horizons because nothing falls across them, and these objects are called dynamic horizons. So we're now going to do these isolated horizons first. And I would like to explain what has happened. So these isolated horizons will generalize the idea of the killing horizon. So basically what it does is, it's a killing vector field is extremely strong global condition. So what isolated horizon notion does is to extract from the notion of a killing horizon only those properties which are kind of very local to the horizon itself, not outside, and which are necessary to, for example, establish the laws of black hole mechanics and such things. So we're extracting from the very, very strong conditions that there is an isometry, that there is a killing vector field, very, very sort of weak part of it, which is really necessary for the black hole itself. Okay, so that's what we're trying to do. Okay, isolated horizons. So how do we do it? So the idea here, as we saw, is that nothing falls across it. Yeah.
So here, when you say nothing falls across, you pull back of a stress energy tensor is zero?
No, the pullback is not zero because, for example, you can have charged black. For Lyson-Osdom space-time, the statement is that you've got a stress energy tensor at the horizon, but it means that TAB times the null normal to the horizon. So that is isolated, nothing falls. So if you take the stress energy tensor, you take the null normal, this is null normal to the horizon. So this quantity is usually the time back vector field, and the flux of energy or something, or angular momentum, etc. will become. So we're saying that this is constant. And this index pulled back to the horizon, so projected out to the horizon. So we're not saying anything about isolated horizons. So the idea is that nothing falls across it, so therefore we want to understand what it is. So let us go back to what we did when we first introduced the notion of the marginally trapped surfaces. So I had this picture up here in which I got some two-dimensional surface, yes, being written as a circle, but it's really two-dimensional surface up here. And then from here I can look at the outward going null geodesics. These are outward going null geodesics, LA. And then there's also going to be an inward going null geodesics. Okay. So basically, given it in any curved space-time, if you give me a space-like 2 surface, I'm assuming it to be S to be a closed 2 surface. A closed 2 surface technically just means it is compact and has no boundary. So I give it to, I always will draw it as S2 because the 2 sphere is the most interesting physical case, but there are some exceptional cases where 3 torus topology can also arise. And if you have positive cosmological, if you have negative cosmological constant, so equidistant space-time, then the horizons can have other topologies. But for us, our universe, if cosmological constant is small and it is positive, so in that case, these two spheres up here are going to be 2 spheres, so I'm always going to be drawing them as 2 spheres. So I got this object up here. And then we introduce a notion of an expansion. So on this 2 surface, we introduce intrinsic metric. It's a plus metric, or SAB, which is a projection operator into 2 sphere. So this SAB is just equal to delta AB plus LA in B minus plus AB. So this is the, so if I take the data is good, this one. Okay, so it is just, this is a projection operator, ln. So this, and then there's a positive definite metric. If I lower the index, I just get a positive definite metric. So then the statement is up here that we could define using this shear and expansion. So the expansion of, for example, the null normal L was obtained by taking the derivative, covariant derivative, 4 dimension of L, but projecting both indices on along the two sphere. So I'll get here SAD and contracting them. And the shear was defined to be equal to SAC, the trace-free part, SAC SBD minus 1/2 SAB Okay. So that was the shear that we saw last time, and we saw understand the expansion. Expansion is the area of these two spheres is increasing here, decreasing along N. So expansion is positive for L, and it's going to be negative for L. And then shear is it doesn't have anything to do with whether the two spheres are expanding or not. It has to do whether or not there is rotation or there's angular momentum here. So that's there is shear. Let us not talk about angular momentum. Just there is a shear. So the null generators are sort of shearing as you go along. And as we saw last time, so these were the two objects up here. And the statement was that for a marginally trapped surfaces, this theta sub L was equal to 0. So there's no expansion. So now there is a simple equation which is called Relativity equation. It's just differential geometry. You can just play around and see what happens. It is true for any kinds of geodesics, but here we're interested in null geodesics. So we're going to look at the Relativity equation. So supposing we start the two sphere like that, and we take this L, and supposing we make L to be a geodesic vector field. So supposing we do it LA grad A B equal to 0. We can always, in other words, I have an L vector field and I just extend it along geodesics up here. So then I'll get a geodesic flow. And along this flow, I got these two surfaces, and therefore I can always take, for example, let's suppose that the affine parameter is V. So this is the affine parameter. So this surface that we started out with could be V equal to V naught, and then I could look at a future surface up here. This could be V equal to V1. And so on these surfaces, I can just define the expansion as shear everywhere. And what the Relativity equation says is that how does this expansion change? So it talks about theta dot. How does this expansion change as you go along this flow? So the time derivative, like motions here are regarded as time, so how does this change? And the Relativity equation, just differential geometry, you play around with. Theta already has one derivative of L, right? Theta has one derivative of L. Theta dot is going to have two derivatives of L, so you write down the expression and you just commute the derivative operators, you get a curvature tensor and manipulate it. And you find that this is just equal to minus 1/2 theta squared plus sigma ADL, sigma CDL times this. You can contract with either the metric, 4 metric, or the 2 metric, because these are already projected. I'll just contract it with let's say CSPD plus 4-dimensional Ricci tensor. So this is a 4-dimensional Ricci tensor of the metric tensor times LALD. Okay, so this is an identity. So this is this identity. It doesn't use any physics, it's just differential geometric identity. That the dot of theta is just given by this equation up here. And this Ricciardo equation plays a very important role in the singularity theorems. It's in fact from the center to the singularity theorem. So one is always looking at what happens to its expansion along geodesics. So it is very important for singularity theorems. Okay. Now what you notice up here is the following. For the marginally trapped surface, if this is a marginally trapped surface, this quantity is just 0. And I told you that what we're interested in is really taking these marginally trapped surfaces and stacking them. So basically, these are all marginally trapped surfaces. We just stack them if I wanted to isolate a horizon. Okay. So we're just going to be marginally trapped surfaces. I mean, if I wanted any of the quasi-local horizons, we're just stacking the marginally trapped surfaces up here. So if you stack, if that is the case, then theta is just 0 everywhere. Theta of v is equal to 0. So for the world tube of marginally trapped surfaces, okay, theta is just equal to 0. Hence, if the marginally trapped surface, if in fact this stack of the quasi-local horizon or the stack of these marginally trapped surfaces is just these 3 manifold. So if this is a quasi-local horizon, if this is a quasi-local horizon, then all of this theta will just vanish. And in that case, so if the world cube is a quasi-local horizon, then theta is equal to 0, theta naught is equal to 0, because theta is equal to 0 everywhere. So that tells us immediately that sigma AB, let me just call it sigma AB squared, plus RAB LAB equal to 0. Remember, sigma is a 2-dimensional tensor. This metric is plus plus, close to sphere. The metric on this is plus plus. SAB is a plus plus metric up here. Therefore, this quantity is always positive definite. And that is why I just wrote sigma squared. And now for the first time we bring in physics. If in fact we have got Einstein's equations, and if the stress energy tensor satisfies the dominant energy condition, for example, so the statement is that now bring in field equations. So far we did not do that. Now we bring in field equations, and then we know that RAB LALB is going to be the same as the Einstein tensor, that's LALB. The reason is because the extra term is just scalar curvature times a metric, but the metric hits this is a null vector, so I just hit 0, and this quantity is equal to 8 pi. We're setting g equal to 1 most of the time. 8 pi times TAB. Now, the dominant energy condition, it says that RAB times LA for any null vector field LA is a path-directed null vector, a path-directed causal vector, not necessarily null. It could be time like or null. So it says it's a path-directed causal vector, which means that if I got 2 null vectors, or if I have 2 causal vectors which are future-directed, then the product is always going to be negative. If this is path-directed, this of course is future-directed. Let me just assume here LA is future pointing. Okay, let's just assume that. Then the statement is field equations will imply that this quantity is path-directed. Therefore, if I take it in a product of the future-directed one, I'll get positive. Future is negative, so future past is positive. Therefore, this will imply that RAB, LAB is positive. But if in fact this null surface, which is spanned out by this geodesics LA, if that null surface had the property that all these sections that I've written down up here are expansion free, so the area is the same, area doesn't change, That's what expansion free means. Then we know that this is equal to 0, but the energy condition says that this is always bigger than or equal to 0, and therefore hence if the null surface let's call this null surface n, just give it a name. If the null surface n obtained by stacking is obtained by stacking the marginally trapped surfaces, if this null surface L is of course the local horizon, then we put these two things together. This one says that the sum is positive or non-negative. This one says that this is non-negative. Therefore, of course, each of them is non-negative. Therefore, the statement. Sorry, this equation says that this is actually 0. I'm sorry, I said something else. But this equation says that this sum of these things is 0. This is positive. This is manifestly positive. So if that is 0, then both of them are 0. Therefore, then sigma AB equals 0. Equals 0. So in particular, the statement is that this will say that nothing is going to be falling across the horizon, because if I take so the statement is that this actually does imply, because L is a normal to the horizon, if I manipulate nothing falls across the horizon. This physical meaning of that is nothing, no matter. Matter does not falls across the horizon. I should just say no energy, no matter energy. Energy or momentum or angular momentum falls across the horizon. So this is so Raichandra equation gives us an obvious way to define isolated horizons. So what I did up here was to just tell you mathematical identity, and then said that let's suppose apply this mathematical identity to the congruence of null geodesics which are emanating from a marginally trapped surface. Then I made an important assumption that let's suppose that this congruence of geodesics, this surface n that we obtain up here, spanned by this congruence of null geodesics, has a property that all of the theta, the expansion, is 0 everywhere, and then that tells us that if that is the case, then in fact it is isolated. So, no matter falls in, and later, next lecture, we'll see that sigma is kind of a measure of how much gravitational wave energy falls across the horizon. And therefore, what this is saying is that this is also equal to 0. At the moment, you don't have to know it, but that's what finally happens. So in fact, intuitively you understand what is happening, that there is no gravitational energy falling across, there is no matter energy falling across, and that is why the area of the horizon doesn't change. It remains constant. So that is the idea up here. That's why theta is equal to 0. So now we can do our definition. So these were, so to say, going back and forth between mathematical identities and physical ideas, and that leads us to the definition. First, we're going to talk about a non-expanding surface. A non-expanding horizon this non-expanding horizon is a null, is a smooth. Everything is going to be smooth, so I will not write smooth all the time. By smooth, we've always been Cn, when n is sufficiently large. We need n to be at least 3, because we would like to define the wild curvature tensor and take its derivative. So basically C3 or more. Typically, it's assumed to be C infinity. So a non-expanding horizon is a smooth null manifold, or submanifold in space-time, such that the expansion theta sub L of its null normal is everywhere 0. So the expansion is 0 immediately implies, so implications, obvious implication is in the area of two-sphere cross-section is constant. And we just saw here, it also says that the no flux of the energy of momentum across this horizon. And for a reason that will become clear in a minute, typically this non-expanding horizon are denoted by delta. Okay. So now the statement is that we'll just call this non-expanding horizon. The delta comes from the fact that it's kind of a piece of the event horizon. Because I won't draw it again, maybe I should try. So if I looked at the Wydra space-time that we did last time, right? We looked at Wydra collapse, so basically we had got some matter coming in from infinity, from sky minus, and then we got here sky plus up here. So the matter flow up here is here, and then we got the event horizon forming here. So this is the Wydra space-time in which there is matter falling in from sky minus into sky plus. We saw this last time, and there's a singularity that's happening. Over here, we got flat space, Minkowski metric, flat space. Over here, there's no more matter, so this is Schwarzschild. And then in between, there is this dynamical region that we saw, which is because the matter is actually falling in here. And we saw that here, the event horizon does form and in fact grow in the flat region of space-time. So this region of space-time is completely Minkowski space-time. And yet the event horizon actually starts, is the event horizon. And grows, is formed and grows in the flat region of space-time. But in this space-time, the statement is that there is no marginally trapped surface here. So questions were asked about it. There is no marginally trapped surface here at all. In flat space-time, there are no marginally trapped surfaces. There is no marginally trapped surface here. And then we actually start getting marginally trapped surfaces here. So this is a non-expanding horizon, and this is called delta. So you can see that delta is only a piece of the whole event horizon. And that is kind of the motivation why we call it delta. It's a piece, not the whole thing. So non-expanding horizon, delta up here. Okay, so now what we want to do is, so that's our first definition, and we want to see properties. So it's a null surface, so in that sense it is like the event horizon. But its area is constant, whereas in the event horizon case, the area is increasing. And area increases because matter and gravitational waves fall into the event horizon. In this case, the area is increasing because matter is falling up here. But as we saw, it can also increase for no reason, no local physical reason. It can also increase because matter and gravitational waves will fall across in the future. 100 million years from today, some matter and the galaxy may collapse and form a black hole, and therefore the event horizon is growing in this room right now. And that could well be the case. But we just don't care, right? I mean, that we don't want to say there's a black hole in this room or anything of that sort. On the other hand, as we just saw, in this room, there is no marginally trapped surface. So there is no non-expanding horizon in this room. Yeah.
Why is there no marginally trapped surface in the realm where matter is falling in?
It turns out, we're going to say it next time, but the marginally trapped surface actually starts forming when the matter comes up here. And so the marginally trapped surfaces, the world tube looks like that. It grows up here, and then it becomes non-expanding up here. So here it is expanding, it's dynamical up here, and this is given by R is equal to 2m of v. And we saw that the Wydra metric is m of v. By the way, those of you who might have missed last lecture, conceptually it was very important. Fortunately, this gentleman, I already put it on the web page, so you can read that. Okay. So that's what happens in that case. So that by the time the dynamical horizon settles down, it is actually null. We're going to see that dynamical horizon is space-like. When it's growing, its area is increasing, and it becomes null when the area stops increasing. And therefore, here we got all these marginally trapped surfaces. each point up here is a marginal trapped surface, but there is no marginal trapped surface in this region up here. Okay, so properties. So first of all, it's nice to have some definition, but does it capture what we have in mind? Right? Does it capture the idea that this non-expanding horizon is really is in some sense isolated? Right? That's what we want to say. Is isolated. So that's what we want to understand, and I think pedagogically it's better to do it in some order. So let me just check what the order might be. Let me do it. Right. The first thing is that what do we have? So I got delta is a 3-manifold, and we got the null normal F. Okay. So here, I mean, in the motivation, I said that we actually shoot null geodesics up here. But in the definition, it makes no reference to null geodesics. It just says it is actually just a null surface, which is given to us, and L is this null normal, right? It is null normal. So this is a null normal. But if you got a hypersurface such that the normal to it is actually, for a null surface, the normal to the hypersurface is also tangential to the hypersurface. So if it happens that the hypersurface is null, and then we got this, which is ruled by this null normal that is given to you, then the statement is that this vector field is always geodesic vector field, not necessarily affine parameterized, but a geodesic vector field. I think probably people don't know this. Is that correct, or people know this? So the statement is that that's what we got. So the first property is that LA grade LB is proportional to LB. Some other values. That is to say, LB geodesic. So I got a 3-manifold. And therefore, this 3-manifold delta, we can say that this is given by some function f equal to constant. So, for example, I could look at u, the coordinate of this is constant. There's some function f is equal to constant because I got a 3-manifold, right? So every 3-manifold is defined by some one-dimensional load. So it's just some function is equal to constant defines the 3-manifold up here. So that means that grade AF is proportional to LA, because LA is a null normal. Right? So F is constant, so its gradient is going to be normal to the surface, and therefore it is proportional to L up here. Okay. Please ask any questions if you have. So what this just means is that if I give you a tangent vector F, PA grade AF is equal to 0, the only this is equal to 0 for all tangent vectors. Tangent vector fields TA, we got this equal to 0. That just says that this tangent, that grade F must be normal, because if it is perpendicular tangent vectors, it is normal. So that just says that. Okay, the LA is the only vector field. Tangent to delta, to null surface, such that GAB equal to GAA. So the null normal is tangent to the 3 surface, but it is perpendicular to every vector in that 3 surface, including itself, because it is null. Okay? So that's what. So this is the first property. Now how do we show that? Well, because we just start by saying L is just given by F times, is proportional to that. So let us suppose that LA is equal to some, let's call it beta times grade F. Right, it's proportional to proportional to grade F. So let's suppose the proportionality constant is beta. Then LA grade A LB would just be equal to beta LA grade A beta LB. Right? I'm not doing any work so far. Now I just expand by using Leibniz rules. So I'll get here LA grade A LB plus plus I'm going to get the other term, which is beta LA grad A. LB. Now what I want to show is that this is proportional to L. But L, as we just saw, is the only vector which is perpendicular to every tangent vector T. Right? T is the only vector field tangent to delta such that it's perpendicular to all T. So L is the only vector field which is for all T tangent to delta, this is equal to 0. Therefore, what I want to show is really that if I take LA grad A LB and plug into it TA, so T is an arbitrary vector field, so if I plug TA into it, I would like to show that if this is this will be proportional to L if and only if this is 0 for every tangent vector field. Clear? No? Yes? Yes. Anybody, any questions? Yeah, I mean, it's not really profound, but okay. So the statement is that the question that we're asking up here, we want to show is that is this proportional to L? LA grad A LB is proportional to L, is the same as asking, is it true that if I take this vector field and if I product it with any vector which is tangent to the delta, all tangent vectors. So this is what we want to ask. So let's just calculate that and see what happens. So we just calculate this, right? What is this? So I just plug T into it. So when I put T into LA grad A LB, LA grad A LB is equal to this. If I put T into it, here I'm going to get TB times LB. And that of course is 0 already. Right? Because T times L is always equal to 0. So I'll get T times L, that is always equal to 0. So I'll be left with just this term up here. So therefore, TB times LA grad A LB. I'm doing this all this excruciating, boring detail. The reason is because people are not used to null surfaces. Null surfaces are a little bit counterintuitive. That's why we're doing it in detail.
How did the beta appear in the equation above the last equation? No, the one below. This one, yeah.
Well, L is equal to, oops, sorry.
Okay.
Okay. Thank you, it's wrong. That's why, that's what people were confused about. Sorry, this is wrong. That's what people. So I'm just substituting this up here, so I'll get here beta times, I'll just type here LA times, not A times beta. It's better now? that's what you're problem. Thank you for asking. So I'm just substituting L here, LB to be equal to this. Okay, so that was wrong up here. So therefore, so this is equal to this. And now what? Now I think everybody understands that this is equal to. The question is, LA grad A LB is going to be proportional to LB. I'm sorry, I always go back to blackboard. Is proportional to LB if and only if TB LA grad A LB equal to 0 for all vector fields tangent to delta. Okay. Everybody okay now? Yeah. Sorry about that. Okay. So this is what we get. So this is what I want to calculate now. So this is just equal to TBLA times. So let me raise the lower indices, just make it simpler. B, there's nothing. I'm just raising and lowering these indices. I'm in 4 dimensions, and I can always do that. You always raise and lower the metric, and the metric commutes to the derivative operator. So this is perfectly fine. So we get this object up here, and that object, as we just saw, was equal to TB LA times grad A times beta. Okay, so I'll just raise and lower T, the index P, that's all. Okay, so now we just use Leibniz rule. So I get here 2 terms. I'm going to get TB LA grad A beta LA grad A beta times grad BF plus LA beta times grad A grad BF. Okay, just using Leibniz rule, and that's all I get. Yeah, if I'm making some silly mistake, please let me know. So now this is just L. TB is contracted with grad BF. F is constant, so grad F is normal to the surface. Grad F is proportional to L, and therefore this contraction is equal to 0 because of this contraction. This term is 0, and therefore I'm just left over here. But now because this is two derivatives, these are symmetric, so I can switch them, and I can write them as BA. And now I see here that I got here LA grad A of F. Right? So I can write this as PB times LA beta times grad B of grad AF. So, but grad AF is just equal to L upon beta. But now, when beta comes out, I'm just going to get TB as A grad B times LA. Plus, when beta stays in, L comes out, but L hits L, and L is null, so I don't get anything else here. Okay. When beta hits grad B, therefore, then L comes out, and I'll get L dot L, and therefore I get 0. So we're just left with this. And now this, of course, is just equal to 1/2 of TB times grad B of L dot L. Right? I'll just get coming up here. L grad L is just equal to 1/2 of that. If you expand this out by Leibniz rule, you'll just get twice this. That's why this is factor of 1/2. But L dot L is 0 on the surface. This 0 on the surface does not mean that grad B of that is 0. But this is 0 on the surface, and I'm really contracting it with a vector which is tangent to the surface. So within the surface, this is always equal to 0. So if I move within the surface, this is equal to 0. This is equal to 0. Thus, what we have shown is that TB times this is equal to 0. For all tangent vector fields, dA to delta. And therefore, the statement is that this implies that LA grad LB is equal to some alpha times LB. Because this is perpendicular to all tangent vectors, so it must be proportional to L. That's the only vector which is perpendicular to all vectors with a tangential. Therefore, by that. So the first remark is that the L vector field is a geodesic vector field. But it is not necessarily finely parameterized. We can do that. We can do that by just rescaling L. We can rescale it so that it becomes a geodesic LA grad LB. We can rescale it by some function, so that define L prime to be equal to some function times L, such that L prime A grad A, L prime B equal to 0. So we can do that. So these non-expanding horizons are ruled that null normal is always a geodesic line. So this like.
What ensures that there is only one node vector?
So the statement is that, yeah, good, very good. So when we say it's a null surface, right? So if there were another null vector, which is also tangential, thank you for the question. If there's another null vector which is tangential to this thing, then I will have two null vectors which are tangential, and the inner product between two null vectors is always, if, let's suppose it's future directed. If not, you just change the sign and make it future directed. The inner product between them is always less than or equal to 0. and is equal, so if it is less than 0, then there will be, okay, then the signature of this manifold that we have got up here would not be 0 plus plus, right? Because there are two vectors, so zero product is -1. So in that case, in fact, the three manifold would be time-black. It would not be null. So if you are given a null vector, if you are given a null surface, then it has its null normal, but there cannot be any time-like vector tangential to it, or any other null vector tangential, because this is null normal, which means that every vector must have 0 in a product with it. And if I get given another time-like or another causal vector, time-like or null vector, then the inner product is going to be, say, strictly negative, unless the other vector is also null and coincides with the first one. Any other questions? Please ask me questions. I mean, people look a little bit puzzled. This is not very profound, so there's no reason to be puzzled. So if you don't understand something, I may be saying something not right, like what happened in that equation. So don't hesitate to ask.
So maybe my intuition is wrong about essentially Lorentz signature or something, but within a three manifold in a 4D space, don't we automatically know there's only one null? Or is it because of Lorentz you can have technically two normals? You
have to show that there are no two normals, right? No, he's not saying the other vector field is normal. I mean, not normal. There's going to be only one normal, right? Because Because, but the question is, can there be another vector which is also tangential, but is null or time-like? And the statement is that in that case, the manifold will not be null. In that case, the manifold would have signature plus or minus plus plus. If it is, then it will not be. Okay. So on a null surface, you always have one null normal and every other vector which is tangential to it is space-like. It's all space-like. So that is why the signature is 0 plus plus. Okay. So the next thing that we want to show is that so the second property, that in fact Liel of this metric, we define the metric QAB. This is signature 0 plus plus on the three manifold. This is just defined to be equal to GAB, pull back to QAB. Now those of you who are not mathematically minded, this pullback seems complicated. I mean, you know what I'm talking about, but it's the most trivial thing that one can imagine. So just let me just tell you. So all this means is that for all vectors TA, PQA, tangent to delta, QAB, TATB. This is the product given any vector field. The tangent is just given by GAB. So QAB, but QAB only knows how to act on vector fields tangent to delta. G knows how to act on any vector field. So in this language, in this picture that I was drawing before, I got this L vector going like that. This was L, and then there was an N vector which is coming in. G will know how to act on N, but Q does not know how to act on N. Q knows only how to act on things which are tangential, and that is why it's called pullback. Pullback just means you forget, you prevent yourself from contracting G with any vector which is not tangential to the three manifold. And then what you get is an object which is intrinsic to the three manifold, that is Q, and that is its property. Now, I just want to, again, because it's good to get very, very elementary things about null surfaces out of the way so you don't get confused. So previously we also talked about a metric S up here. I also talked about a metric SAB, which is equal to GAB. It has signature plus plus, GAB minus twice AB. So plus. I think I made a mistake last time. I put mine, I wrote it plus first, and then change the sign. So second thing was wrong. The sign should have been plus and not minus in the definition of SAB up here. Okay, because if I plug into, they are both future directed, so their inner product is equal to -1. So if I plug into it LA, then I will get, here I will get LB, and here I will get minus LB. In fact, there is a plus sign here because the inner product is -1. Okay, so I also have this S step here. So this S is tied to this surface whereas the pullback is not tied to anything. To talk about the pullback, I don't need to have a two surface. But to talk about S metric on the two surface, I need the two surface, of course, right? So this is knows our Ashtekar, but does not need a specific two surface S. Whereas this, the SAB that we talked about, which is the two-sphere metric, and typically with the metric on a two-sphere, that metric does need a particular two-surface to talk about. But if you give me, for all vector fields, let's call it SA and S tilde A, tangent to S, where I got SA S tilde A times SAB. This metric up here is the same as the SA S tilde A GAB. But since these two S and S tilde are in particular tangent to the three manifold, they happen to be also tangent to the surface, then in here we know that GAB, TA, T tilde, when T is any vector field tangent, this is true, so this is also equal to SA S tilde A. So, if there are tangent vectors, so Q only knows how to operate on tangent vectors to the three manifold. S only knows how to, it's a metric on the two sphere. And the statement is that if you restrict yourself to tangent vectors up here, you will get the same answer with S as you will get with G, as you will get with Q. Again, I just don't know if it's all too trivial or whether it's worth saying it. Right? It's okay? You got it? So these are all things about the two manifolds, about the null manifolds, and then now we can go ahead and make sense. So the statement that have the third property, so QAB is the second property. QAB is supposed to be the metric. So QAB is the degenerate metric. Of this null manifold delta, its intrinsic property, and of course QAB, LB is equal to 0, and that is why signature is 0 plus. QAB's cap is annihilated just by the null vector L and by no other vector. So that is so QAB. So signature is +1. Okay. All right.
By a trivial typo, just so people don't get confused.
Yeah.
The last line of the board you just finished, the SA S tilde B.
Thank you.
And similarly throughout.
Thank you very much. Thank you. Please correct me because I think I agree with you that things can be confusing. SA is still down. So I call them S because they're tangent to this manifold, and SAB is a metric on the two manifold. So S always refers to that two manifold. Okay, so QAB is degenerate metric, and now the next property is that L of QAB. Now this will be a homework problem, but I'm going to tell you how to show that. It's not very difficult to show. So basically, the statement is that QAB, as we saw, is the pullback of GAB. So therefore, L of GAB, of QAB, is the same as L of GAB, pullback. So you're given a tensor field, and you're pulling back to the manifold. Okay. So So this room is a manifold. Think of this as being a submanifold. Everything should be one higher dimension. This should be 4-dimensional. This should be 2-dimensional. But sorry, this should be 3-dimensional, but it's only 2-dimensional. Okay. But let's suppose we are in this room, and then the statement is that I take the metric in this room and pull it back here. Pull back metric is just a fancy way to say that the tensor field knows how to act only on vectors which are tangential here. So I get some metric up here. Now what I'm going to do is I'm taking a lead derivative of this metric. Now L is tangential to this surface. So the lead derivative is well defined within these two surfaces. Okay, L is completely well defined in this surface up here. But now however what I can do is, I know that the metric Q here is a pullback of the metric in this room. Pullback of the metric. So I can just extend this L any way I want outside, keeping it tangential here. And I can now consider a diffeomorphism in this room. I just map the metric to along these diffeomorphisms. That's what we're doing by lead derivative. That's the infinitesimal action of the diffeomorphism. So I can take the metric and then evaluate at a point and pull it back. So I can act by the lead derivative and then pull back. Or I can just pull back the metric and act on the lead derivative. Since the action of the diffeomorphism on this manifold is the same, because this is a vector field which is tangential to the two manifolds. The two things agree with each other, so the statement is that therefore this is the same as dl of GAB, pull back. But we all know what this is. This is just 2 times grade LB symmetrized pull back. This is just thing. So that is to say, what we want to show is that if you give me any vector fields which are tangential to the 3-manifold delta, tangential to the 3-manifold delta, then I want to show that this object. So I want to show that this is equal to 0. That is to say, I want to show that this is equal to 0. That is to say, I want to show the pullback of this is equal to 0. That's the same as saying that this object equal to 0. So to show this is the same as this, or like if this equal to 0 is the same as asking if this is equal to 0. So now what you can do is you can consider here is a horizon that is given to you. Or I can just draw it now just like that. So this is our delta. Just to sort of visually say that the area is not changing. This looks like time lag, but it's actually null. The vector field here is L. And the area is not changing up here. And then what I'm trying to ask is, what I'm asking is it true that TA T tilde AB, grade LB symmetrized is equal to 0? Well, what you can do is, given any vector T, I can write it with we don't need a metric for that, uniquely as a vector along LA, say alpha times LA, and a vector which is in these two surfaces. I just choose some two surfaces. So this is a horizontal vector. So the statement is that I can always write TA as alpha times LA plus some horizontal vector. This is tangential to this 2-manifold S that we got up here. And similarly, T tilde A, alpha tilde, and X tilde up here. Then you can just plug up here and then expand and use LA grade LB is proportional to LB, and the shear of L is equal to 0, and the expansion of L is equal to 0. That would imply that T tilde A, T tilde B, grade LB equal to 0. In fact, for your exercise, you might just forget about this symmetrization altogether. And even this is true. Okay? Just use the fact that this is shear, that the L is shear free, L is expansion free, and it's geodesic. And you want to show that this is equal to 0, because this is equal to 0 is the same as this is equal to 0. Why? because linear of QAB is the same as linear of pullback of GAB, which is the same as linear of GAB whole pullback, which is really the same as 2 times grad A LB pullback. And this quantity will be 0 if and only if the contraction with any tangent vector fields is equal to 0. And that's what we are trying to show. Take a tangent vector field, expanding it in these 2 ways, and just expand it out, and you'll see that because this is important, precisely if this is cheap, to get null geodesic is cheap, because given any null surface, L will be a null geodesic vector field. So this will be always be the case. And then it will not be the case that, the metric will be Lie drag. But because the expansion is 0 and the shear is 0, then the statement is that the metric is actually Lie drag. So this will be a homework problem, and these are the steps that we have. And in fact, what we are going to show in the homework problem is that this is equal to 0. You don't even need a symmetrization up here. It is just equal to 0. And just use it. Just plug in, expand out. You just have to understand each step there. Okay. So we saw 2 properties. One is that it is geodesic, and the second is that QAB is Lie drag. Now, what does it mean QAB is Lie drag? Now we are getting some physics out here, because QAB is the intrinsic geometry up here. The intrinsic geometry doesn't have to be that of a 2-sphere. The intrinsic geometry can be rippled, can be quite complicated. You know, the area is constant, but it can be quite complicated. Can have any multiple structure. In fact, we're going to see again. I hope to do it today, but next time we'll see that in fact this geometry has many multiples, and in fact when the black holes first collide and the new horizon is formed, in fact that manifold would have very complicated structure. But even if a black hole settles down, we have Kerr uniqueness theorem. So if there was nothing else in the universe, then this geometry will settle down, and it will not be a round 2-sphere, but it will be the 2-sphere like on the Kerr horizon, which has a certain amount of distortion. It has a certain amount of multiple moments. So this cube has a lot of information that we're going to see in a minute. By the way, if we have, last week we had all this PAX meeting, and we had all these very beautiful talks, and we heard that in fact, when the 2 neutrons are collided, and then finally the final black hole form, there is an accretion disk around it, and the accretion disk has about 10% of the mass of the black hole, of that order, a few 6%, 7%. So the multiple moments of the horizon in that case are not those of Kerr. They differ because this accretion disk distorts the black hole horizon. The multiple moments are going to be different, and how can you calculate them and so on, we're going to see next time. So these multiple moments, even for the isolated horizon, when the black hole settles down, the multiple moments are not necessarily those of Kerr, if in fact there are accretion disk or magnetic fields. Another calculation that 2 students here at that time, Steve Fairhurst and Badri Krishnan, had done was they found, they did a very nice paper about these isolated horizons. They found that if you have a black hole in a uniform magnetic field that is given to you, then in fact, again, the multiple moments are distorted. But for a 10 solar mass black hole, they found that if you have 10 to the 17 Gauss magnetic field, then the multiple moment distortion is 10%, which is quite a lot. And yesterday what we were told about was that in these collisions, the magnetic field that are produced are of the order of 10 to the 15, 10 to the 16 Gauss. So it is not quite 10%, it's going to be 1% or 0.1%. But these are physical effects that have to be captured when LIGO becomes much more sensitive. And that's why I'm doing all these things in great detail. So you will be able to do calculations. I could have just stated these things, but I would like you to be able to calculate things, and you will be able to see what is multiple.
Abhay, can I ask a
Yeah.
physically motivated question? Namely, if you have, let's say the Kerr black hole is axisymmetric, and if you have an accretion disk around it, which is also axisymmetric, then the full geometry has to be axisymmetric,
Sure.
and then it has to be Kerr geometry.
No. This is the big mistake, right? There is no uniqueness theorem, right? Sorry.
Oh, yeah, okay.
There is no uniqueness theorem for the
Okay.
Schwarzschild. There is uniqueness theorems. If it is spherically symmetric,
Yeah.
then it has to be Schwarzschild outside. But if it's axisymmetric, there's no reason for it to be Kerr. In fact, there's infinite family of solutions known, right? And which is the Weyl solutions, which is not rotating, but a complete solution is no, and they include this accretion disk and so on. But then the black hole is not rotating.
I thought the uniqueness theorem fails only for certain kinds of fields. I mean, you were saying,
No, no,
giving
but
examples of those Young-Mills fields.
Yeah, because those are the fundamental fields. So I was talking about Einstein-Maxwell theory, Einstein-Young-Mills theory, and so on and so forth.
Right.
And there what we saw was that uniqueness theorem would fail if you have Einstein-Young-Mills theory, but then Young-Mills field would have to be in a phase which is not confined, but is force of like 1 upon R. That's the statement. So, sorry, I get excited. Excuse me.
That's fine. I mean, that's precisely what we want to know.
So the statement is that so if you have just a regular perfect fluid, a matter, there are disk around it, then the solution is not Kerr. Kerr is uniqueness is proved for vacuum solutions. Period. There's nothing else. I was giving examples of even when you have fundamental fields, it is not. If you just have perfect fluid, because of wild solutions we knew it was not true. But the question was, if with fundamental fields, does it fail or not? Okay. So just 5 minutes and then we have to quit. So okay, this is what we do. So what this tells us is very interesting thing. It says that yes, we didn't really ask for it, but in fact, yeah, 1 minute. We didn't ask for it, but we found that in fact the 3 geometry that we had is the metric that we got with is also time independent. So we wanted to talk about something is isolated, right? And we just saw that if in fact you've got non-expanding horizon, then nothing is falling across it. But does it mean that the geometry of the horizon is not changing in time? The answer is yes. So that's all I want to say. So that the second property implies, thus, the metric QAB of relation 0 plus, and its curvature. Its curvature is what calculates what encodes the Maskell multiple moments, and the statement is this is time independent. So in this sense, the horizon is in equilibrium, in the sense not only is nothing falling into it, but in fact it fits the fact that the intrinsic 2 metric, so it's not only that the area is not changing. I mean, there are many ways in which area may not be changing, but the metric might be changing, because area has very small information about the metric, right? Metric is 3 components, area is only 1, area form even is only 1, and total area is a global quantity. So what we have shown is that surprisingly this simple looking definition captures the idea that the metric itself is not changing in time. Okay. And then we'll continue, next time we'll just finish what this all tells us and talk about multiple moments. And if there's time, begin with the dynamical situation. Okay.